So my name's Tom Beach, and I'm from Optimise AI. I'm going to be presented today on how we use digital twins to optimize energy and carbon performance of non-commercial buildings. So just a little bit of a background is we're a startup, a spin out of Cardiff University. So I myself currently dual hatting. So I'm part of the time I'm an academic at Cardiff University. The other part of my time I am the CTO of Optimise AI. So what I'm going to talk about today is how we are building a system using digital twins, as I said, to help building owners save energy in their non-commercial buildings. So we started operating in January of this year. So we're really actually very recently active. And the real problem we're trying to solve is that 90% of non-domestic buildings don't have building energy management systems, and those that do generally lack actionable insights. So there's a big issue across the sector in that building owners have very little visibility on what's actually happening with their building data, in terms of they can't understand how all the data they're getting from any management systems they have, if they have them, translates into things that they can actually do to save energy and improve the environmental performance of their building. How do we do this? So we build a digital twin that makes use of quite a few different sources of data. So you've got the building itself. This is the physical asset. We take data from the BMS system, other data sources that may be available. These could be sensing systems that are already in the building, smart meter data, and any other sources that the building operator has available. We fuse that with BIM, various data sets and building use information that we've collected, and we use simulation, generative AI models to actually help understand the building energy use, predict future building energy use, and produce actionable insights for the user based on that information. Through several trials we've done through the university, we've achieved from 20% to 35% savings in energy. So this has been tried, tested and validated, underpinned by scientific rigor. So while we've been only operating as a company realistically from January 2024, the work actually we've been doing has been tried in a variety of use cases, which we've got scientific publications in, and the software that we're using as Optimise AI very much originates from the original research software developed by the university. These were just kind of three of our use cases that we've explored over the last few years with differing values of energy savings. We've made quite considerable progress in the few months that we've been operating. We were awarded the 2024 winner for Tech Startup Award from the Wales Technology Awards. We've secured funding from Carbon 13, the Department for Energy Security and Net Zero, as well as Welsh Government. We've also got our first clients, and the list of them are down there. And so we're currently in the process of building our platform with these friendly clients with a view to launching publicly for the wider industry later this year. Very much our digital twin approach is sort of summarized in a little bit more detail on this slide, and very much we kind of fuse several different types of modeling here. So we have a building model, which is a BIM. We have a visual model of the building. We have an energy model. We have various artificial intelligence models, and all these are fed via a variety of different data sources. So we have sensors, smart meter data, and we've deployed these in a variety of the buildings for our clients. And our two kind of key outputs that we attempt to get and we attempt to deliver are these two things here on the right, which are our implementable energy optimization scenarios or dynamic energy optimization scenarios. So these two things consist of, the first is a series of suggestions and advice that we give the users, telling them how they can modify the configuration of their building or their building systems to help them save energy. This might be along the lines of you can reduce the temperature set points in certain spaces, reduce your hot water temperature. Generally, these are kind of one-off or infrequent changes that they can do to improve their building's energy uses. And these will generally be implemented by a human, but prompted by our system. We also have dynamic energy optimization scenarios. And these are where things actually get far more interesting, because this is where we're working towards a system that can dynamically control things in the building, such as dynamically altering temperature set points, dynamically, say, opening and closing window shadings, dynamically turning off and on various building systems in order to save energy. This might be by reducing when systems are needed, activating cooling earlier to prevent the building overheating, putting shades down to prevent solar gains, or even moving and shifting loads into cheaper times of day when possible. Now, at the moment, we are looking at human and/or automatic implementation of these. And the idea is here that in some cases you can directly actuate things in the system, in a building system, by remote control. So you might have motors or other actuators you can use, or you can have more dynamic prompting. The idea concept is someone might have a mobile device and you can submit a sort of nudge to that device telling them they need to go and change this setting actually in the building to achieve optimum energy, a message to the facility manager or something like that. And that's very much our approach. We've looked at actually, sorry, I'm going to give a quick demonstration in a second, which will demonstrate some of the work we've done with our first few clients. And all these clients, what we're focusing on is building up an initial data set of information that they've got, then using that to produce these actionable energy insights. So I think I've got 2 minutes left, so I'm going to switch over to my browser to show you the optimized web platform. So this is our example demonstrator that we built for Network Rail and Connected Places Catapult, which is Bristol Temple Mead Station. So as we can see here, we can have we've constructed a 3D model of the station. I can zoom in, I can zoom out, I can rotate, move around, rotate it like this so we can see all different angles of the station. This is really just here for visualization, but it really helps customers kind of ground what they're seeing in the actual building that they're looking at to understand it visually. We provide annual energy consumption, so this is generated based on real meter data. This cost here is just exemplar because I'm not going to put the actual Network Rail energy costs in something in public, so I've just put in some random figures there for the purposes of this. And this graph here shows the energy data that we're getting and our model data that we're predicting their future energy consumption. Because our data is based on a BIM model, we understand the structure of the building, so we can drill down into various different aspects. And we try and, when possible, make use of data that we can capture to make this visual and data based. So if, for example, if I can click here, I can click on the subways of Bristol Temple Meads, and I can zoom in here and see an internal sort of panoramic photo of the subways. I can do the same here for one of the tunnel spaces. I can zoom into particular zones in the building. For example, I can click on this mess room here and I can see an internal photo of this mess room. And when I'm on this view, it also brings in different sensor data for the sensors that we've deployed in Bristol Temple Mead. So I can see the CO2 level in this space, relative humidity, temperature, and luminance. One of the other really interesting things we can do is we can integrate with BIM data sets. So if I click on this model view, this will take a few seconds to load as it's having to load a BIM model. But here we can see inside the model for that given space within the building. And again, here we can see the different sensor data that we've got for this actual building. So we can see motion, CO2 level, temperature, relative humidity, and luminance. So we're collecting all these data from these sensors with a view for using it for future energy optimizations in the platform. And what we can also do, we can zoom back out and look at block level. So Bristol Temple Meads is divided into several blocks, and we can see estimated energy breakdowns of each of these blocks. I think I might have run over by about 30 seconds, but thank you everyone, and I'll be happy to take questions at the end.
So our first question here, Tom, is to yourself. It says, we saw Google's smart building targeted with a denial of service attack when the temperature was raised, so people left the building. How are you securing the input and connected traffic to ensure that the dynamic changes you're suggesting are not targeted?
That's a really interesting question. Is one of the challenges we kind of have to face when we've done this in the past. The way in which we've kind of set it up is to have systems in the building call out to our servers periodically, so the transmission is outgoing as opposed to incoming. To the building to actually receive these updates, because we can actually understand these updates will come at periodic intervals. So we'll set kind of an optimization horizon, and so we might then be expecting new parameters hourly, daily, or something like that. So the building system we would set up when we set things up inside the building to call out to our servers to get the requests. Now, generally speaking, what we've kind of looked at in the past, there is obviously still the risk of a denial of service attack. For example, if a denial of service attack happens to our servers, then obviously the building can't retrieve any new configuration. And generally what we've kind of explored with that is it would just continue using the last known configuration that it had. So we're thinking here these might be like patterns of when blinds should be opened and closed, or patterns as to when set points should be changed. And that would probably not be energy optimal, but would be safe. And that's the kind of approach that we've kind of taken so far, in that by having the transmission going from the building to our servers, the building actually is not exposed or expecting any direct input itself, and you can then kind of use conventional sort of practices to secure it behind firewalls, etc.
Very good, thank you, Tom. Our next question again for you is a very interesting offering. How long did this implementation take, and what was the payback period for this project?
So the first bit is kind of easy to answer. So we literally started implementing in January. So what you kind of see is what we've got so far, and we've been building this up with this initial set of customers. Payback period for this project is really too soon to say. I mean, ultimately what we're doing is we're building a product here we're wanting to release it to customers kind of later in the year, so it's really kind of too early to see. I'm not sure if you're asking about the payback period perhaps for the energy changes.
Yeah,
so
maybe.
just in case if that was the question, some of the changes we'll implement and you can see immediate improvements. So some of them, and quite a number of them, are kind of one-time kind of savings for that. But one of the advantages in our system is it shows you your expected monthly or annual energy savings. So we'll be able to come up with a predicted energy saving for a given month or a given year, and then the customers themselves can use that to dictate, or not to get to decide on what whether they want to adopt it or not. Some of the scenarios are I say free to implement, in that all you need to do is task someone to go down periodically and change settings. It could even be a one-off change of setting. Some of them do need investments in terms of you might need to put sensing systems or control systems in, and in which case you can view the amount of energy you expected to save with the scenarios and weigh that up against the expected cost to put the sensors in or put the control systems in, and kind of weigh it up in that way.
Very good, thank you. Another question, Tom, for yourself, if I may.
Yeah.
Do you think the modeling the BMS using AI off premises has any consequences? For example, many buildings often have a BMS capability to operate at a higher energy class and more dynamically than they currently do, but on premises, where is the balance?
So certainly in the buildings we've looked at so far, we haven't seen many I don't think we've seen any BMSs that are actually being used in that way. Even buildings built in the last couple of years, from our experience, are quite closed systems, and realistically, unless you're adopting some of their own software tools, are quite limited in what they can do. So for most of them, the way we've been approaching it is to do everything in the cloud, and then communicate this, or have the systems in the building go back up to actually connect data. Now, what we are looking at as well is possibly kind of doing a hybrid approach, so having some capability in the building itself, so like installing one of our a control unit kind of on the edge in the building itself to do some stuff to do some work on premises to allow for faster response, and then communicate back to the cloud. However, I guess from a business sense, the amount of buildings with these up-to-date BMS systems are probably already pretty energy efficient, and they're not really our kind of core initial market. Where we're getting a lot of interest is buildings that are maybe 5 years old, 6 years old, 10 years old, where the BMS systems are literally more than data reporting, if they even have BMS systems. Um, and those are the building users that have really got the appetite to actually want to save energy. And so that's actually where we're focusing at the moment, rather than the real cutting edge of buildings, which are already pretty good if they've been built to modern regulations. And so, yeah, we'll probably look at them later, but initially, the kind of the slightly older buildings are where we're focusing most of our effort.
Very good. Thank you, Tom. So a lot of questions for you today, Tom. So the last one here, if I may, is what class of building do you target? Only class A? Answer, any non-commercial buildings, especially essentially we only exclude residential at this point.
So someone's pasted this in here. Someone asked this in the chat, and I answered it in the chat. So I think someone's just put this in there. But so essentially, the only type of building we're excluding is kind of domestic buildings. So we're not looking at kind of your domestic houses. We're not looking at your sort of blocks of flats and things like that. In the kind of grey area, we have looked at a few, so sort of things like university halls of residence and stuff like that. We've looked at them, and things like hospitals and care homes. Yes, we've looked at them, but the only thing we're kind of excluding at the moment is your kind of blocks of flats and your individual domestic houses. Although at the moment, I will say we've only really been going since January. Our initial use cases have been kind of university type education buildings, so like your lecture type buildings, a couple of railway stations, and some office buildings.